This is a CAMX 2020 education session. Thank you for attending this year's virtual conference. My name is Larry Christy. I'm the Director of Research and Development for Veelo Technologies. Today's education session is titled Advanced Heating Solutions for Accelerated Adhesive Cure. Veelo Technologies was founded in 2009. We are headquartered in Cincinnati, Ohio. We have about 20 employees. Our core business is around engineered materials, specifically for aerospace and defense. We deliver differentiated capabilities, mostly high-value customers and applications. Again, engineered materials for composite aerostructures is our core competency. This kind of falls under three buckets. We have electrically conductive materials, including electromagnetic effects, survivability, notably lightning strike protection and EMI shielding. And then we're also looking at thermoplastic welding, whether that's inductive or resistive. The second bucket includes heated solutions for composites. This includes bonding aerostructures, accelerated adhesive cure, which is today's topic, composite repair, heated calls for improved debulk and compaction. And we're also looking at heated tooling for out of autoclave and out of oven processing. The third bucket includes non-metallic de-icing, whether that's fixed wing leading edges, rotor blades, engine inlets, or a secondary bond application. Some background on our current product offering. Veelo Veil, we've invented that in 2016. It's a metallic carbon fiber non-woven. This is used for lightning strike protection and survivability. The non-metallic de-icing, it is a carbon-based system, electrothermal de-icing. Most notably improves fatigue and strain to failure. It's also a lightweight option and more energy efficient design capability. The third would be a product that we invented in 2018. This is our VeeloHEAT Blanket. It's a silicone-based blanket. Again, it uses a carbon-based electrothermal element as well. And again, it's used for composite manufacturing, composite repair, and bonding. In today's topic, we are going to discuss the accelerated cure. Our heater blanket uses a carbon-based electrothermal film. This is a continuous film. It might be different than you might find in the market with metallic filament blankets. This actually leads to a more energy efficient blanket as the whole film is heated up, as opposed to the metallic filaments really have a spacing between the elements. It's also much more conformable and drapable. The non-metallic nature of this product leads to fatigue resistance. We can mold it into custom shapes. Again, the continuous film is more scalable and conducive for larger tools or blankets. And then because it has this continuous network of, these carbon conductors, it is more damage resistant. If the carbon conductor gets damaged, really there's still an electrical pathway for this blanket to operate. Whereas if a metallic filament blanket were to work harden or break or short out, then that's a single point failure mode. So what is VeeloHEAT Blanket? It starts with our carbon-based electrothermal film. The resistivity of this material can be tailored. We do this by varying the loading content of the carbon conductive material that we use in the film matrix. We are able to achieve single-digit resistivities up to several thousand ohms per square. The sheet resistance of this film is engineered to meet the design requirements of the in-use blanket. Typically, this is at 5 watts per square inch power density. Next, the film is integrated into off-the-shelf silicone film. Because of this continuous nature of the heater film, we're able to achieve a very high uniformity in the heat profile in the final product. Here are some examples of some past projects that we worked on using our heating solutions on, in this first case here, some three-dimensional structures. This is a stringer. We had to apply some heat here for a bonding application. The next one is a kind of a net-shaped heater for a rotor blade repair and processing. The third is very applicable to this topic. It is a pretty unique blanket that has some holes for some fasteners, and then this is for accelerating adhesive cure of gasket materials. Also, recently, within the last 12 months, we've developed custom controllers. We've got a lot of good feedback on these, and we use these very often in our internal development for these heating solutions. I'd like to next show the basic structure of our heater blanket and some considerations for designing these blankets. The silicone-based blanket, we would have first a layup of and design of electrothermal film. We would then have bus bars on opposite ends of the blanket. We would then tie into our wires and terminations there. Often this is done with a crimp connector. Some things to consider for requirements for Veelo for your application are the dimensions and geometry of your heater profile. What's the application temperature? What's your available power? How much power do you need for this to heat up your part? Definitely need considerations on where we might place the bus bars. Is there any material compatibility concerns? And then any durability concerns. Some other features that we've got asked and is to consider as a multi-zone blanket. For 3D blankets, do we need to do a net-shaped blanket here, or are we going to rely on the drapability of the blanket? And then do you need a custom controller for your application? So the next step, once we have all the requirements for the heater blanket, we would design the electrothermal film. Based on the power input and the available power and required power density and the dimensions, we are able to calculate the sheet resistance of the film that we need to manufacture. So power, as you know, is voltage squared divided by resistance, and then this would be equal to the length times the width times the power density of the heated area. So for a case study for a 12 by 12 inch heater at a standard 5 watts per square inch, this ends up being 720 watts. So calculating or solving for resistance, we end up here with 20 ohms. And then for sheet resistance, that is going to be resistance times width divided by length. Because this is a square in this case study, we ended up with 20 ohms per square sheet resistance target for this electrothermal film. So once we have that number, we would send that off internally, release that design, and then we would manufacture that film for this product. So if you're not familiar with what sheet resistance is or the unit ohms per square, I hope this helps. In terms of sheet resistance, the resistance of the material or the film, sometimes it's called surface resistivity. Again, the resistance is defined as length divided by width times sheet resistance. So in the case that the length and the width are equal, then the resistivity, or the resistance is equal to sheet resistance. Another way to correlate this is that sheet resistance is equal to resistivity divided by thickness. So going back to our 12 inch by 12 inch heater blanket design case study, we found that we needed to manufacture a 20 ohm per square electrothermal film. How we would do that is we would tailor the content of the carbon in that film. So in this case, we have a curve built out. We would need roughly 7.5% loading to achieve that 20 ohm per square target. So then once we have that formulation, we would send it off for manufacturing. So what's really different about this electrothermal film that's carbon-based? Well, comparing this to conventional metallic filament design, we kind of have some slits here that show in the case that the blanket is damaged. In the case of the VeeloHEAT material, you can see, if you zoom in close, you can see the continuous carbon film there. And then looking at the conventional metallic filament, you can see the cross-section here of the serpentine filament design. Most notably shown in this slide is that this continuous carbon network, this blanket will actually still operate in this damaged condition, whereas the metallic blanket here either is just not going to turn on or could even present itself as a short risk in a fire hazard. The next step after we manufactured a blanket, we would inspect it for uniformity. We do 100% inspection using a test method for SAE ARP 5144. In our case, we use a infrared thermal imaging camera. Once we've taken a picture at the 350 degrees, typically, we would analyze the image. To pass under the specification, there's a 2-inch pitch, and then we would exclude actually the 2-inch edge band around the blanket. And then to pass this requirement, we would need to be within plus or minus 10 degrees at 250, or most notably for our internal testing, 350F. So here's an example report of infrared testing on one of our 12-inch by 12-inch blankets. So after we've taken that image at the blanket at 350F, we would export that image using the FLIR software package. We would export to a CSV file. Then we would take that CSV file and we have a macro using Excel that we would filter out the 2-inch band around the blanket. Next, we would basically break that filtered image into 2-inch blocks. We would then take an average of each block and report that here on the right in figure 3. And then our macro would average that 2x2 grid and report a temperature range. In this case, we are seeing a range of just under 4 degrees, 3.7 degrees here. That's well within the plus or minus 10 degree requirement for this SAE test method. Another comparison to conventional metallic filament blankets versus VeeloHEAT Blanket. On this slide, you can very notably ascertain where the filament serpentine design is. Zooming in, you can see those hot filaments, and then the spacing between each filaments is really quite cold. So we did a IR analysis here, a line across that image, and we are seeing upwards of 40+ degree temperature variation, depending on if you're on that metallic filament that's heating up, or you're between the metallic filaments. In a real case scenario, we have 2 thermocouples kind of randomly placed on the blanket. Again, we're seeing a 27 degree difference between thermocouples there measured. This really does lead to some TC placement issues and reliability and placement. So compared to the VeeloHEAT blanket with a continuous carbon heater film, as you can see that there's no spacing or cold zones because of that continuous carbon network. Similarly, zooming in on the IR image, we have some analysis here of a line across that. Much reduced, we're seeing a 10 degree range here compared to the 40 of the metallic filament blanket. Again, we did 2 thermocouples laid on the blanket, and we're only seeing really a 2 degree difference between those. So this really leads to a much higher confidence in the TC reading, and ultimately this yields improved process control. The next couple slides, I'm going to overview some of the other capabilities of the VeeloHEAT blanket. As I mentioned earlier, this silicone blanket can be net shaped. So here's a case study for a blanket that we designed and then made a prototype. This is for bonding of a stringer hat. This shows a blanket with a gradient power density. This blanket was actually pretty recent design. We were able to tailor the resistance across this film and actually achieve a gradient temperature profile. This was developed for a customer who had issues combating edge effect cooling of their part caused by just natural cooling or just thickness variation. The final capability I'd like to mention is our custom controller offering. We developed this around 12 months ago and actually presented this at CAMX last year. A prototype. Since then, we've shipped several of these units to customers. We are really taking either the customer's requirements and then tailoring this temperature controller to fulfill their needs, or we are pairing this temperature controller with our technology to provide a holistic heating solution. I very much believe that the reviewed background and understanding of these capabilities are paramount in providing a heating solution for accelerated adhesive cure and bonding applications. Here at Veelo, we are not adhesive experts, but we are working with partners in the industry to meet aerospace and defense needs and working towards reduced cycle time and improved throughput. So what is adhesive bonding? Adhesives are used to fasten two surfaces together and included materials like glues, epoxies, and other polymer agents that bond by evaporation of a solvent or by curing of the bonding agent with heat, pressure, or time. Here you can see an image of a custom blanket prototype that we designed for a customer looking to accelerate the bonding of a gasket material. It has through holes designed for accommodating fasteners and indexing pins. On the right here, you can see an IR thermal graph of the blanket with the through holes. So we did a case study with this customer on gasket bonding. Their process is a room temp process. It took 7 days to complete one part, and then using an array of these custom VeeloHEAT blankets, we were able to demonstrate the same gasket bonding strength in only 1 day. So we achieved this by using a 120-degree Fahrenheit elevated temperature with our blanket and a custom controller, and this was used to accelerate just the curing process of this room temp adhesive. So recently we had an internal need to actually accelerate bonding of some surface mount fasteners to our silicone blankets. We received an order of 100 plus blankets that required these fasteners. This is for the customer end use mounting application. We had a requirement for a room temp vulcanizing silicone adhesive. This was specified for bonding the stud to the blanket. This from the supplier recommendation for the adhesive is a 24-hour cure, and then we had a 4 to 8 hour post cure for this adhesive. Using elevated temperatures, we were able to accelerate the adhesive curing process. We initially demonstrated this with just our ovens, but soon realized that we really preferred to use our ovens for manufacturing the heat blankets. So we did a internal case study on a custom 1.1 inch and 1/8 diameter heat blanket, and that was designed to mate against the surface of this the stud and then apply heat locally, again achieving a reduced cure time of only 2 hours. So the implementation of these heaters, we were able to save 22 hours per blanket of manufacturing time, and also ensuring that our oven remained open for manufacturing, which is really the intended purpose for our ovens of these heated blankets. Ultimately, this led to a reduced lead time of 2 weeks for this project to our customer, and they were very, very pleased with that. The next couple slides, I have some design details for this internal case study of mounting the surface mount stud to our own heater blankets. So again, this was a 1.125 inch diameter heater that was intended for accelerating the cure of these RTV silicone. Here on the image on the left, you can see a little bit of foreshadowing of what the final blanket looked like. The power leads out there are the white color, and then we also have integrated thermocouple here. That's the black wire that you see coming into that blanket. In this case, it was a J-type thermocouple. We had a couple designs for the electrothermal film that we wanted to look at here. The first was just a basic single film that kind of arced around the ring of the blanket. Next, we had a serpentine design. And then third, we had 2 concentric films. The reason why we did that is we anticipated with the single film design that there would be a temperature gradient as the path length on the inner diameter of the heater is much shorter than that of the outer diameter. Here on the image on the right is kind of a mock-up of the heater blanket mounted to the stud. Next, you'll see the electrothermal film lay up in assembly here in the middle. Again, the left is the film designs that we're looking at here. You can see the black material there is the carbon-based electrothermal film cut out per the design specification. There on the right is the completed blankets. We took some IR thermographs. You can see that we did see the anticipated result with the single film design where the interior of the blanket is hotter than the outer diameter of the blanket. In certain applications, this might be preferred, but for our internal need, it was not. The second 2 designs, the serpentine and the concentric film design, were relatively similar temperature gradient, temperature deltas, although that the concentric film seems to be the best overall uniformity. Next, we tested our configuration to validate the concept. First, we placed a second thermocouple underneath the fastener and the blanket to test the surface temperature, and then we clamped the stud and blanket to the carbon plate. The blankets were tested to ensure that the target temperature was achieved. During this process, using our controller, we also were able to set the PID parameters and then also perform function testing of the integrated thermocouple. We did see some variation between the integrated thermocouple and the surface temp, so we made note of that during our subsequent testing. So here on the right, you can see the test setup using now the RTV silicone adhesive, and then also the blanket that we were bonding the studs to. So here you'll see, again, the clamps. In the background, there is a fastener that does not have tape on it. This is the room temp control. The 3 on the right there have tape on them, simply so we can observe under IR the temperature of the washer there on top that's clamping the blanket to the fastener, just because the metal has low emissivity. Here you'll see some IR images of the blankets under the test. Here on the left, we got the 3 blankets at 120 degree F hold, and then there on the right is a 220 degree hold. You'll see all the blankets appear to be relatively the same. Pretty good uniformity. Happy with that. One of them does appear to be a little bit hotter. That must be due to the thermocouple placement within the internal of the blanket. Here you'll see a video of the fasteners after the cure cycle is completed. A summary of this particular result was a 2-hour hold at 220 degrees F. We did do a 5-degree-minute ramp rate for this. You notice that the application of the adhesive may have been a bit generous here, but the results speak for themselves. So here for the first one is the first design, the single film. See the technician here is showing that the adhesive is no longer tacky, sticky, that it is indeed fully cured. Second image there is a concentric film. The third here being showed is the serpentine film design. fully cured, no tack. There, the X is the room temp cure baseline. You can see it's very soft, non-surprisingly, still gummy. Of course, this is a 24-hour cure system, so this is exactly what was anticipated. So having demonstrated a proof of concept with the RTV silicone adhesive mounting the stud for our internal use to our heater blanket, we decided to do some testing on an epoxy adhesive system. In this case, it was a 24-hour room tip epoxy. So we did the same setup. We bonded the same fastener to a carbon fiber panel. Same panel actually that was shown earlier during the validation testing. Here we have a side-by-side baseline with no heat, and then we are using the serpentine heater here because we felt like the temperature from the thermocouple matched the surface temperature the best. So there on the right, you'll see the temperature, the blanket during the test. We did a 200 F degree hold. Again, but for this one, we only did a 15 minutes per the supplier recommendation for this epoxy. 15 minutes at 200 F was adequate for 100% cure. Again, here a not so surprising result. More temperature equals a reduced cure time. So there on the left is an image of the bonded fastener using our heater blanket at 200 degrees. Again, 15 minutes here. We observed a very hard epoxy here, no residue, was not soft at all. No indication that it wasn't 100% cured. And there on the right was the room temp baseline after 15 minutes. Clearly, being a 24-hour full cure system, it was still tacky. It was flaking off during touch. Clearly not fully cured. So the results shown here in this tutorial showcase the efficacy of accelerated cure using these small heater blankets, custom heater blankets. Really though, this is just proof of concept testing. Next steps are more of a systematic approach for testing these and validating that they work. So really the next steps for us are first perform actual mechanical bond testing to validate that we are achieving equivalent or better bond strength using the elevated temperature cure versus the room temp cure adhesive. Specifically, we want to dig deeper on the epoxy systems, and we like to perform an actual degree of cure analysis to validate that the effectiveness of this accelerated cure using the blankets. We'd also like to test some configuration using higher temp epoxy systems that might open up some other applications, might be useful for some repair scenarios. And then fourth, we'd like to do some in-depth case studies with some external customers to validate efficacy of this approach, and then also the value proposition. We believe, the math makes sense that higher temperature equals, shorter cure and therefore reduce cycle time and improve throughput. But we'd like to build a better case around that, and then broaden our application base a bit further. I'd like to thank you for watching this education session titled Advanced Heating Solutions for Accelerated Adhesive Cure. I know this year's CAMX has been a little different with the virtual experience, but I appreciate your attention today and spending your time with me on this topic. Please reach out to me for further questions on accelerated adhesive cure or other composite bonding applications. My email is larry.christy@veelotech.com. Also, feel free to reach out to me on other questions for your composite processing needs, or to further discuss Veelo's capabilities and custom heating solutions. Also, please visit our website at www.veelotech.com for further information about Veelo Technologies and our product offering. Thanks again.